Hi, Dr. Lalish.
Hey, good morning. How are you?
Good. Can you hear me over
Yeah.
okay.
Yeah, sounds good.
Okay. I have questions on the homework, and stuff from the lecture that
Okay.
I guess. Um, for the first question, I think I derived it correctly using like the square root of r, but I'm still confused about like replacing r squared with the x squared plus y squared. But I'm still confused by what you mean when you said it's like circular.
Okay, yeah. So let me, maybe I can illustrate that. Let's see, let's try this. Oh, I gotta plug in my tablet here, hang on. Okay. Now. Okay, so, all right, so, we're all familiar with the idea that the one-dimensional Gaussian is just that kind of shape. Now, if you think about it in 2 dimensions, so if we were to kind of try to draw it this way and say this is x and this is y, and so the value of the function would be kind of a surface on top of x and y, then if we look at it, and I'll just kind of take a general form like this. Okay, so first of all, the maximum of that function has to occur when x and y are 0, right? Because then that becomes a 1, and any values other than 0 basically cause this to be less than 1. So basically, oops. So it's a maximum of 1 there. And then if you were to set, let's set y equals 0, and trace it out along x, then it's going to kind of look like, well, it's the Gaussian function just along x, right? If y equals 0. And then similarly, if x was equal to 0 and we were to kind of trace it out along y axis, then it would look like a Gaussian function along y. And in fact, because this is in terms of x squared plus y squared, and yeah, okay, over sigma squared, give it that, then pretty much any axis you chose through the origin of that, and if you traced it along that axis, it would look like the same Gaussian function. And so if we were to kind of do like a contour plot of how this thing would look in 3D, as a 3D kind of surface, then you'd have a hidden surface behind. It would kind of look like that. And all of those contours would be circular. Okay, so, this is, another way of looking at what a 2-dimensional function might look like. And of course, as I usually display them, right, in the form of a 2-dimensional image, we just kind of flatten that out, and instead of doing a surface in Z, we are just displaying intensities, and so that's much harder to draw, of course, and so it kind of is brightest at the center and fades away. But my point about it being circularly symmetric, or the term, term that gets used a lot is isotropic, meaning same in all directions. Basically says that, if I did a cut through this thing at any, well, that was a bad one, through the axis, through the origin. If I did a cut through this thing at any direction, it would look the same. And so that's what I mean, when I say it's circularly symmetric or isotropic, that's what I mean. It's the same in all directions, okay? The difference, and so because of that, I can do the substitution r squared equals x squared plus y squared if I want to. And just say, oh, you know what? If I write this in terms of polar coordinates, then it's that. Okay, and it has no dependence on the angle part of the polar coordinates, right? A polar coordinate function would be in terms of r and theta, where theta is the angle, but this doesn't depend on the angle, which makes it isotropic. Does that help?
Yes.
Okay. The other point I should make that I didn't make to you, but I made to other students, is that full width half maximum, when we talk about full width half maximum, it can only be measured along one direction. Okay. I guess I didn't point that out explicitly in class. It's kind of implied in how we would do it, but because of that, you need to kind of pick an axis along which to measure it, right? And so it really, full width half maximum has to be measured along one dimension. So you kind of have to take that two-dimensional function and decide, I'm going to measure it along, x or y or some other direction. In this particular case, because it's isotropic, it doesn't matter what direction you pick, right? You should get the same answer. Or if you generalize it in terms of r. So you could set y equal to 0 and do it in terms of x. You could set x equal to 0 and do it in terms of y. You could substitute in r. You should get the same answer regardless. And then the only other thing I'll say, I think, about that is if it's not isotropic, anisotropic would be the right term for it. In other words, not the same in all directions. Then it would be of the form e to the minus 1/2, where x squared has its own sigma x, and y squared has its own sigma y, and those two could be different, okay? And if that happens, then these contours don't look like circles anymore. It's longer or shorter along one direction and looks more elliptical. Okay, if they both, if both of these are equal, if sigma x and sigma y are equal, then we have this isotropic function, and we just kind of generalize it with a sigma, and it looks circular. Even when we display it as an image, it looks circular. But if this is the case and these two are not equal, let's say sigma y is larger than sigma x, then it's going to stretch out more along the y than the x, and it's going to look more elliptical than circular. And in fact, we could even, this isn't the most general form, because we could even rotate it to where it's along some axis that is not x or y, but we won't get into that. Okay, does that answer the question? Okay. All right, let me get out of that. Okay. What other questions?
Number 2, I was a little confused of how to use, I'm assuming the 1D Fourier transform properties you're talking about is that worksheet. I was confused of how to use those to get the PSF for the low pass filter.
Okay, so yeah, so let's talk about that. So this is a ideal low pass filter. And so if we were to look at it, let me bring back my drawing sheets here. So if we were to look at it in the Fourier transform space, right? So I'm gonna, so U and V, this is a frequency space. And basically this thing is a square where this is all equal to 1 and everything else is 0, right? Okay. So, so one thing to recognize is that you could write this as the multiplication of two one-dimensional rectangular functions. So if I was to look at this along U, for example, it looks like that, right? It's the rectangular function. And similarly along V, and it's in fact, it's the multiplication in U and V of that same function. Okay, so we could kind of write it that way. Let's call this, you know, sometimes they refer to that as a rectangular function of U, and we'll call this a rectangular function of V. And this does cut off at what we defined as omega and omega 0. Okay, so that's the kind of the picture of what that looks like in the Fourier space. So if we're talking about, and if that's the filter's MTF, right, or I guess technically the OTF, we're trying to basically invert the Fourier transform here. Okay. So first question is, do we know the inverse Fourier transform of that function? This is one of the ones that, you know, well, certainly in my other class, this is the one of the ones I ask people to know, at least in general. About the sinc function? Yeah. Which is sine x over x, and basically looks kind of like that. Okay, so more or less what I'm asking us to do here is to say, okay, if, let's say, we could write h of uv as I'll try that. I think we understand what I mean by that. We could write it kind of that way and say, oh, okay, you know, those are two separable rectangular functions. And if I'm trying to find the point spread function, which is going to be the inverse Fourier transform of H, then, you know, how can I use all those other facts to get there is the point. Okay.
Okay.
Yeah, and basically, you know, you're going to, because this is a separable function, you're going to be able to separate the 2D Fourier transform in, you know, x and y uv into inverting the one-dimensional Fourier transform in x and in y separately, because this is a separable function. And so it's going to be, basically some product of sinc in X and sinc in Y. All right. Does that make sense to everybody? And I don't think I don't think I asked for the exact relationship. Well, show what it would be. Yeah, kind of. But the more important stuff is, okay, what happens as you change that cutoff frequency omega naught as you move it higher or lower? What happens to, you kind of need to know what that, probably look up the sinc relation with the rectangular function and use that from a table and use that. And then think about, the property, kind of the scaling property by changing omega naught, what happens to it in the spatial domain. That's more or less what I'm asking people to just describe, qualitatively, but using the math to kind of get there. Does that help?
Yeah, it does.
Okay. What else?
Just to clarify, so is the point spread function always h of xy?
Well, if I'll be careful. If h of xy is the response of our system to a point, and so usually I label it that way because for whatever reason h got used for that a long time ago, and people typically use it. Then yes.
Okay.
As long as the context is right, yes. In general, that's what I would use, and so. Yeah, but again, what that means is in the name. Basically, h of xy should be what you get out of the system if you were to introduce a point source, whatever that is, at the input, right? And so in an imaging system, if you were able to image a point source, then the image that you get at the output of your measurement system is the point spread function of that system.
Okay.
Okay.
In the notes we had f of x going into h of x, and then the g of x was coming out.
Right.
So is the system response g of x in that case?
No, the system response would still be h of x. So from a language standpoint, I would say f of x is the input, g of x is the output image, and h of x is the thing that describes what the system does. Okay. And technically that should be described as that should be called the point spread function. If I make a mistake sometimes, maybe not. But it's fair to call that the system response, although I will say system response might imply more the frequency response in the Fourier domain. In other words, capital H of UV might be, could be called the frequency response of the system, right? System response is a little more generic, and I guess could be either one, point spread function, frequency response. Does that? I know that might be a little confusing, but
yeah, that helped. When I was thinking system response, I was thinking the output, so I was just getting those terms confused. And that makes more sense.
I can see that because it's the response of the system to a certain input.
Exactly. Yeah.
Sure. Yeah. We try to be careful. I try to be careful with the words I use for things, but I could slip up on that one sometimes. So context matters, right?
Absolutely.
Yeah. Okay. Any more?
It's for the same question. When you mean the edges on the image, are you talking like the examples that you had in class?
Well, so this goes a little bit to, well, when people look at images, or when we use our visual system, we are most sensitive to edges, that is, places where the intensity changes. And that's how our higher visual system uses edges to define objects and therefore understand the scene. This is an object and that's an object, and then I, kind of use my experience and stuff to understand that this object is separate from that object and where they are relative to each other. So when we look at, we observe images, the same thing happens. And so edges are really important, okay? And so the point here, and almost none of that matters, but I just wanted to bring that up. But the point here is that, so remember, if this is a filter, it's going, we're going to use it as a system, and so we're going to put an image, use an image as input to it, and take the output of that thing. So the question is, what is this going to do to high frequency features like edges in an image? In other words, what, so, and again, if we go back to the fact that this is going to have some kind of effect like a sync function. So we're going to be taking our original image with its nice sharp edges and convolve them with this. And again, I'm not really looking for people to sit down and do a convolution, but just kind of think about, okay, if the input, there it is, okay. If the input to that thing, let's say, is something, well, we can just say a line, right? We can just say, okay, if I put a line into that system, which, again, we'll call it H, then what is convolving a line with something like this going to result in? And that's kind of the question. That's the thing I want people to think about a little bit. Okay. And hopefully it's not too hard to see, because again, this is a delta function in one dimension, right? And that's the response for a delta function. So I'll kind of leave that one hanging unless there are more questions. There you are. Okay, any other questions? I think I'm probably going to poll the class to see if there's a suitable time we could just kind of schedule off like a Q&A session like this, on a regular basis. Let's see what might be, if there's a good time for everyone. Not sure that's going to work, but we'll try. Okay. But in the meantime, feel free to get in touch, and then we can just do this on the fly. Okay, any other questions? Anybody? Going once?
I have
yeah,
one more question about 5.
Yeah.
I wrote it out mathematically, and to me, it seems like we'd almost need to know more about the filter. So I guess I'm confused of what I guess the question is, how does a linear filter affect the NEQ? I guess I'm confused of what you're looking for what the effect is.
Well, to put it another way, does it change the NEQ of an image?
Okay.
So if you had, basically it's a kind of signal to noise ratio. So if you take an image that has noise, right, and using the equation for the NEQ and how the linear filter would, and so basically what I'm saying is, okay, we can express the NEQ of the input image as a, a signal to noise ratio, and that's basically where you're starting from. And then if you put it through a filter, and could be, we're not using a specific filter, so the filter is just going to be some H of UV property. And using the input-output relationships for the power spectra, because the NEQ is defined on the power spectra, what does that become at the output? What is the NEQ? The ratio of the signal to the noise. And basically, does it change it? If it does, how? If it doesn't, does it matter?
Is in the notes, there's the NEQ is defined with like the H of UV only affecting the signal and not the noise. In this problem, is the linear filter the H of UV, or is that the Q?
Let me bring that up. Let's see. So, okay. I because this is labeled as G, right? So based on the earlier stuff, SGG would be SFF with an H plus some noise. But actually, I think what I'm saying about that is, oh, no. Okay, right. No, so the linear filter, if I want to be consistent, the linear filter is this guy.
Okay, that makes a lot more sense.
Yeah. So that's the best way to look at it. So we're starting from here. So so we have an NEQ at this point, right? And not knowing what these are, we're just kind of talking very generally about that. But the question is, okay, how does the NEQ change in going from here to here?
Okay.
Okay. Yeah. I probably that could be more clear. Okay. And that way you'll get the answer I'm looking for. Right?
All right. Thank you.
Mm-hmm. Okay, any more? Going once, going twice.
For number 6, when relating, I think it's resolution and noise.
Right.
I guess I'm a bit confused about a quantitative example. Like if you have like an example of that.
Oh, of this process?
Yeah.
Well, that's actually a really good point. And we could probably use this. So we did that in signal processing. We kind of demonstrated that, right? But I one thing in this course, unlike that course, I steer clear of doing a lot of MATLAB stuff, because to me that's not the point so much here, but I'm thinking about that. So, however, let me draw it here, right? So, I think, I hope it's, fairly clear that if we have so we're in the frequency domain, and again, I'm just drawing this in one dimension, but I think we understand that as I change the cutoff of a low pass filter, right, and make it less and less, then the resolution gets worse. right? Because it's going to basically blur out the full width half maximum, or blur out the point spread function more and more and more, and so the point spread function is going to spread more and more and more. Okay, so that process, hopefully, it's clear. That process will cause us to go up along that axis. And then similarly, the thing I want to show, and maybe, again, this is not quantitative, but hopefully it makes the point pretty well. And by the way, if, we could do this demonstration quantitatively, I just can't do it right now. Right? That if the noise is white noise and has this spectrum, that as we apply low pass filters to it, then the noise power spectrum is going to follow the filter. And so it's going to go like that and like that and like that and like that. And the total noise power is going to be the area under that spectral curve. And so as we're decreasing the cutoff of that low pass filter, we are moving this way with respect to the noise. So that's the maybe more detailed way of arguing why this thing goes that way. And so we could, if we wanted to do a numerical demonstration of that, what I would do is basically take those Gaussian functions, those two-dimensional Gaussian functions, and basically run, well, start from a point, right? Or I could do it with an image in general, and a noisy image, well, an image and a separate image of noise, and basically demonstrate this as we, run through different cutoffs of low pass filter. That's what I would do if I had the time to do it. Is that fair? Okay. Any more questions for today? All right. If not, I'll see y'all tomorrow.
Thank you.
Sure.
Thanks for
Have
the
a
time.
good day.
You
Thank
too.
you.
Mhm.